Right. So what we've got here is an ultrasonic thickness gauge. Because like I said, if you know the speed of the ultrasound waves through the material, then and we can measure the time, and your distance over time equals speed, or just, you know, you can rearrange that formula basically. I just need to pull this out and put the batteries in it. I don't think they're in there. Then, and what I've got here is an ultrasonic thickness gauge, which will just tell us the thickness of a metal. Okay, because if you've got a casting and you don't know how thick it is, you know, if I want to measure the diameter of those specimens that you did, I just use a pair of verniers. But a few years ago, we had a massive rig in here. It was very old and it had to be scrapped because it was, you know, not being used, and sort of the technology was out of date. But we didn't know how heavy it was. Okay.
Did you get a lot of money for scrap?
No, not that. Well, I think about 100 quid. So it wasn't brilliant. It was better than nothing. So paid for the Christmas lunch sort of thing. That was about it. Okay. So. So we didn't know how heavy it was, and it wasn't just the scrap value, it was the actual getting the thing out, because we have to tell the people who come and remove it, we have to say to them, well, how heavy is it, because they need to bring in the right equipment for it. Okay, so how could we work that out? Because we've then got to say to ourselves, there's not the batteries in there, we've got to say, well, how can we work this one out? Well, because it's a great big casting, we knew the outside dimensions, but we didn't know the inside dimensions. So I could use this ultrasonic gauge to then get the an idea of the thickness. And if you know the thickness, you can work out the volume. If you know the density of the material, which was cast iron, so it's quite easy to look up, density times volume gives you mass. So we could work out the estimated mass of the casting, we knew how many tons it was then, and then we could get in the people with the right gear to do it. Okay, so I'm just going to put this end in here, like that. I need to find some sort of metallic material. Actually, we'll just use it on there. Obviously, I could measure that. So I'm just going to put it on the couplant there. You've got to put on the couplant because it's it's like, you know, we see it in hospitals when you have an ultrasound. I mean, a lot of us have had ultrasound. So you've got this on here, and it's not just babies. I mean, I had one a few years ago for various things. You know, they can see all sorts of things. It's really clever, the ultrasound they do in hospital now. So if we put that on there. Right, that's telling me I'm getting 8.85 millimetres, okay? Because what's happening is the ultrasound pulses are firing out from here, they're hitting the bottom of the specimen, and then they're going back up. So you can say that the distance over the speed equals the time, and then they can work that out in terms of millimetres, okay? The only problem with this is you've got to tell it how fast the pulses are in the material, because if it's steel, they travel at about 6,000 metres per second. In concrete, it's about 3,000 metres per second. In air, as I'm talking to you now, it's about 340 metres per second. So it's 10 times quicker in concrete than what it is in air. Okay, and that's all down to the density of the material. So again, if I wanted to use this one over here, maybe. I want some more jelly actually. 13.9. Okay. And just looking at that, that's that gap there, it's about ½ an inch, so that's about right. I could measure it if I want to, but and the problem with the casting is you've got all the lips and everything, so it's quite good for that, because you can go around the thing and you can actually get the different measurements. And whereas with a pair of verniers, you can't get a pair of verniers in there, so it's very, very useful for that.
Does that not detect any cracks in the material?
No, this is purely thickness only.
Right, okay.
But we have got other stuff here.
So if there was some cracks in there,
you wouldn't. No, it wouldn't all. It would go bypass that, because they would all go past the crack and not really. Yeah, the crack's very small. It wouldn't pick it up. But we have got some new kit which I haven't had a chance to look at yet, which does do crack detection. Because again, if you've got a crack halfway and you put it on the oscilloscope, you can see you'll have a blip there where you've got the crack. So again, you can use it for detecting cracks in materials. Okay. Obviously, we've got X-ray as well. You can do that. We haven't got X-ray here, but we've got. We used to like about 40 years ago, but it was health and safety. Don't like that sort of thing now. Yeah, we've just bought actually an X-ray fluorescence camera, and that camera will actually tell you the composition of materials. But again, we've got to get our radiological protection officer sorted out until we can start firing at things. So once that's done in the new year, then hopefully we can start using it on our castings and materials. Okay. The other thing that's worth looking at, which I thought I'd show you today, is what's that? Yeah, that's what. Right. So, is something called spectroscopy. Okay. Now we can use the electromagnetic spectrum to look at things, and also if you think about things where there's heat involved, you can use the infrared camera. Okay. So what I'm going to do, I'll just ball that up again quickly. I've got a temperature probe here, okay, hooked up to my data logger. There. If I touch the end, you'll see it starting to shoot up, yeah? Because obviously my body temperature is higher than that as the outside. So, flick that off. And what I'm going to do is just take that out, and I'm going to dip that in there without trying to burn myself. Shut that very quickly. And you can see here the data logger is racing up to 95, 97, 98, 99. So nearly 100 degrees Celsius, because obviously the water's just boiled. So yeah, now we're hitting 100 now. Okay. And obviously it'll start to cool down. So what I can do, I can switch on my FLIR camera, which is the infrared camera. And I can then point it at the kettle, okay, and you'll probably have to pass this around to see it. But if I just, oh yes, I've got it plugged in. Just unplug it. If I show this table first, can you see the kettle there? The lid appears red, and the temperature on the lid is telling me is about.
I've seen that police camera action.
Yeah, slightly different to the ones they use on there. The ones they use on there are much more expensive. These are about 6,000 each, but the ones the police use go up to about $250,000 because they're really sophisticated. Okay.
See a fella high bit bit.
Yeah. So this is about 75 degrees Celsius. Okay, that one there. So if I show you, what I have to do is come all the way around here now, and if you look at that, you can see the kettle. Yeah, you can point people. You can see the. Now the interesting thing with this kettle is, if you point it at the metal part. It actually goes green, and it's telling me on the metal part that the temperature is about 29 degrees Celsius. Now I know that's complete rubbish because that kettle's just boiled and that's metal, so it's got to be 80 degrees Celsius. The problem with the camera is the camera's actually picking up my reflection and my body heat, and the metal's reflecting it back into the camera. So the plastic lid comes out really accurate, and if I open the top there, you should be able to see that the lid is bright red now. Okay, so I'll bring it round here as well, so you can. Okay, so you see the lid.
So how does that tell you how thick metal is?
It doesn't tell you how thick anything is. It just tells you the temperature. But if I point that inside the kettle now, it's non-destructive because I'm actually analysing the material. I'm seeing how hot it is. So, and if you think about if you've got some brakes in a car that are wearing, you can see the heat giving off. So that's telling you that obviously there's a problem. So if we look under here, we've got about 75 degrees at the top of the kettle where the steam's coming out, and the lid is obviously cooler, it's about 60 degrees.
Because they use these in the Formula 1 coverage,
yes,
now, aren't they?
Yeah.
In car camera.
So
you see the brakes
yeah.
heated up.
So that's why these are really useful. So it's non-destructive testing, because we're actually looking at the wear patterns in an electronic circuit. If you've got a part that's not soldered properly, you could get overheating. So again, they can use it to look at that in electrical circuits, or transformer that's oil cooled. Okay, so they are very, very useful, but they can give you the wrong value sometimes, because if you're looking at metals, sometimes they're reflecting the heat from other sources and they're not telling you the heat of the source. So if that was a plastic kettle, okay, then that would be fine because it would give me a really accurate value. But because it's a metal still, stainless steel on the outside, it's not giving me the readings that I should be getting. So you've got to go on quite a lot of training for that actually. Okay. So that's a few bits of NDT equipment. So hopefully that'll be enough for your assignment. I'd hope. Okay. And then you've also got to do some impact, haven't you? That's
that's okay.
Yeah, that's fine. What I'll do is just go and get the specimens. Actually, I need to check.